So in this mind map series, what we're going to discuss now is thermodynamics, and before actual thermodynamics, there's this part of heat transfer and radiation that we'll be discussing right now. Now, getting before into thermodynamics, we should have some idea about temperatures and all. So temperature is basically a measure of how much does the uh, heat energy the body possesses, right? Let me just yes. Hmm. So how much the body possesses energy in the form of heat? We have some parameter to define that, and that is called temperature. It is independent of the nature of the particle. So we have different units for measuring temperature. It was because many independent scientists were working on devising a standard unit for checking the heat of the body, and that's why they came up with different units, and some of them are still prevalent today. The SI, first of all, the SI unit is Kelvin, and the temperature ranges from 0 to whatever Kelvin. The least temperature that is possible is 0 Kelvin. And there is this another very popular unit of temperature, that is degree Celsius, and the least amount of temperature that the body can have is minus 273 Kelvin, and to a maximum of whatever temperature. And there's another temperature unit. SI unit is only Kelvin, which is called Fahrenheit. So what we'll do is quickly look into how, and there is another thing called R. We do not need to worry about it because it's pretty obsolete, and only Kelvin and Celsius will do. But just for the safety, we'll also discuss about the Fahrenheit. So first of all, when you want to convert, let's say you have been given the temperature in degree Celsius, then temperature in Kelvin will be equal to temperature in degree Celsius plus 273.1, and this is Kelvin. All right. In the same manner, if you have been given the temperature in degree Celsius, then uh, temperature in Fahrenheit will be equal to temperature in Celsius plus 9 by 5 into, I think there must be some, yes, 9 by 5 into temperature in Celsius plus 32 degree Fahrenheit. So these are the two conversions which you must be familiar with, or you must remember, and this one is the most important. In many cases, you will directly be given either Kelvin or degree Celsius, and you will need the another one, although the Fahrenheit also is very important. So this one part is okay. I think we also discussed thermometer. It is nothing but a device to measure the amount of heat that the body has. That is pretty much what temperature is all about. A thermometer defines temperature. Now coming to yes, thermal expansion. Now, first of all, let's discuss the theory part a little bit. Let's say there is this material in which we zoomed into it, and we got atoms. Now, due to it having some temperature, of course, there must be some temperature, maybe 10 degrees Celsius or whatever, then all these particles must have some kinetic energy in the form of vibrational kinetic energy. That is why it is having some heat. The the moment we say that it has some heat inside it, or it has some temperature, non-zero temperature, non temperature which is greater than 0 Kelvin, then it has some energy in the form of heat, and which is at the atomic level a vibrational kinetic energy. So the atoms are vibrating about their mean positions. All right. Now what I do is, maybe heat it up. I I give more heat into the system, and due to which the the heat energy of the system must increase, and the temperature also should increase. And when the temperature increases, the vibration becomes more, or the vibration gains more amplitude. And due to it gaining more amplitude, these two atoms are now coming closer to each other, due to which it will repel more. And this will result into each particle needing more space for higher degree of vibrations, and as a result of which, result of which, the intermolecular distances now has increased. What this means is the distance between two atoms has increased, and subsequently all the atoms in the particular material will expand, leading to length expansion, area expansion, and density as well. Now, the way we, let's say there is this linear material of length L and temperature T naught. What we do is increase the temperature to T dash. Then the new length of the material L dash will be equal to L naught into 1 plus alpha T dash minus T naught, where L naught is the initial length and alpha is a constant which we'll talk about. T dash is the final temperature and T naught is the initial temperature. This is the formula which you should remember. While alpha is the coefficient of linear expansion, coefficient of linear heat expansion. It depends on the nature of the material, not the dimensions. Now, let's say you have a sheet. If you heat it, then some length will increase in this direction. But in this direction also, the length will increase. Even this length should increase, because we already talked about that the intermolecular atoms, और the जो एटम्स के बीच में जो डिस्टेंस होता है वो इंक्रीज हो जाएगा, क्योंकि हमने ऊपर देखा था कि एटम्स जो हैं वो ज़्यादा वाइब्रेशन करने लगते हैं, उनका एम्पलीट्यूड बढ़ जाता है. उसके वजह से the area should also increase, right? If any area, it contains of length and breadth. If both length and breadth increases, then the overall area should also increase. Then in this case, let's say the area initial was A naught and temperature initial was T naught. The temperature final is T dash. Then the new area A dash becomes initial area multiplied by 1 plus beta into T naught minus T. Very similar equation जैसा हमने ऊपर लिखा है, right? बस इसमें difference ये होगा, the only difference will be that in the place of beta, which was, or in place of alpha, which was coefficient of linear expansion, there is something called coefficient of area expansion. Coefficient of area expansion. Alright? अभी देखते हैं हम एक cuboid है. There is this cuboid. If you provide heat into the system, the length will increase, the breadth will increase, while the height should also increase, because all three dimensions will be governed by the same logic जो हमने ऊपर डिस्कस किया था कि हीट देने से इंटरमॉलिक्यूलर डिस्टेंसेस इंक्रीज हो जाते हैं. तो इंक्रीज होगा तो सभी डायरेक्शन में इंक्रीज होगा. दैट इज वाई द वॉल्यूम विल ऑल्सो इंक्रीज v dash, and the formula for that will be v dash is equal to v naught, which is the initial volume, multiplied by 1 plus gamma into T dash minus T naught. While gamma is nothing but coefficient of volume expansion. These are the three formula, very very similar to each other, easy to remember. आप थोड़ा सिमिलैरिटी लगाएंगे, अल्फा बीटा गामा की जगह एक्सचेंज कर दो और pretty much the equation remains the same. They have been written in the in another format but they are basically the same thing. यहाँ पर जो भी लिखा हुआ है ना, जो मैंने एक्सप्लेन किया, एग्जैक्टली वही चीज़ है, बस उसको अल्फा और बीटा और गामा को एक्सट्रैक्ट कर लिया है इस इक्वेशन से, और कुछ नहीं किया है. Now there is this relation between alpha, beta and gamma, which is the coefficient of linear expansion, coefficient of area expansion, and coefficient of uh, volumetric expansion. That alpha is to beta is to gamma is equal to 1 is to 2 is to 3. इसका मतलब अल्फा अगर मान लीजिए 10 है तो बीटा 20 होगा और गामा 30 होगा. दिस इज फॉर श्योर फॉर एनी मटेरियल. यू जस्ट हैव टू नो अल्फा, और बाकी बीटा एंड गामा आप कैलकुलेट कर सकते हैं आसानी से. आई थिंक this part has been dealt with. Now, thermal stress. अभी आई थिंक हमने लास्ट चैप्टर में पढ़ा था अबाउट द प्रॉपर्टीज ऑफ सॉलिड, इन विच अगर हम पुल करें दोनों साइड से विद एफ फोर्स डिस्ट्रीब्यूटेड ओवर द एरिया ए, तो क्या होता था उसके क्या बोलते हैं, द स्ट्रेस एंड स्ट्रेन वाज डायरेक्टली रिलेटेड टू ईच अदर. एफ बाई ए इज इक्वल टू यंग्स मॉड्यूलस इनटू delta L by L. Now, the thing over here is, I think the same cheese is given. The same thing is given here. Only in this case, what happens is, let's say you have heated it, or maybe there is this situation in which the rod has been fixed or stuck between two walls, और इसको हीट किया गया है, हीट किया गया है, ठीक है. अभी हीट करेंगे तो इसका जो चेंज इन लेंथ आएगा वो तो हमारा आसानी से इधर से निकाल लेंगे. कहाँ गया, हाँ ये द चेंज इन लेंथ, और द चेंज इन लेंथ if the boundaries were not there, that could have been easily calculated as in the format of alpha into t naught or t dash minus t naught. ठीक है. अभी यहां पर क्या हुआ है, एक्चुअली the length has not increased, but due to it not increasing, or why is it not increasing, because there is this wall which is stopping the length of or the increase of length. अभी होगा क्या, this rod will apply some force. ये force लगाएगा दोनों साइड because ये expand करना चाहता है, it wants to expand, but the boundaries of the two walls are not letting it expand. So what I'll do is I'll calculate the change in length or the possible change in length it would have experienced if there was no wall, and I would plug it here. और मुझे यहां से मिलेगा F by A is equal to यंग्स मॉड्यूलस इनटू डेल्टा L by L. जब मैं ये इक्वेशन लगा दूंगा ना, then I will get to know what is the force that this wall is getting, or the wall is experienced due to the force due to the expansion of the rod. ऑलराइट, तो यहाँ पर दो कॉन्सेप्ट यूज हुआ है, एक ये वाला कॉन्सेप्ट और द प्रॉपर्टीज ऑफ सॉलिड एक्सपेंशन ड्यू टू स्ट्रेस. वो दोनों को एक साथ कंबाइन करके इस एग्जाम्पल में एक्सप्लेन कर दिया मैंने. Although it is given in a very short format, but the context in this part has been explained to you. Now, coming to specific heat. Now, what it is talking about. See, let's say I have this block of any mass m and I provided some heat into it, Q. Now, due to this heat, how much the temperature will rise? That is our main thing. Let's say the temperature initial was T naught, एंड व्हाट इज द फाइनल टेम्परेचर गोइंग टू बी, ये हमें पता करना है. तो हम क्या करेंगे बेसिकली, सी Q is nothing but m c delta t, where delta t is nothing but m into c into uh, t minus t naught. ऑलराइट, जो फाइनल टेम्परेचर था इनिशियल टेम्परेचर से माइनस कर दिया, और वो हो गया चेंज इन टेम्परेचर मल्टीप्लाइड बाय दिस द मास ऑफ द बॉडी एंड मल्टीप्लाइड बाय अ कांस्टेंट which is called a specific heat capacity. Heat capacity, it is defined as, agar if we have one object, a homogeneous object, let's say maybe iron, and you provide whatever heat it needs to raise the temperature of the body to 1 degree Celsius, and the mass of the body that you have taken is 1 kg, which is the SI unit, then that amount of heat which was needed to raise the temperature by 1 degree Celsius is called as specific heat capacity. All right. This is called specific heat capacity. Confuse नहीं होना है with something called heat capacity only, not specific, only heat capacity. इसमें क्या करते हैं पता है? कुछ नहीं. The same formula we will write, बस इसमें I'll write it as HC or maybe HC, heat capacity into delta T. मतलब क्या किया मैंने? M और C को combine कर दिया है, और that will account for the heat capacity of the body. It means कि this was independent of the mass of the body, right? Independent of the mass of the body, only depends on the nature of the material, the whatever physical characteristics it has. But this will depend not only on the nature of the material, but also on the mass of the body, because HC itself is combination of mass into a specific heat capacity. All right, ये कम यूज होगा, बट दिस थिंग विल बी वेरी वेरी यूज. आई मीन कितना ज्यादा फ्रीक्वेंसी इसका होगा, यू कैन नॉट गेस. Okay, so this was specific heat capacity and heat capacity that I have explained here. This is dealt with, and now molar specific heat capacity is the same thing. It's just that कि हमने यहाँ पर mass लिया था. See, where was it? Where is it? Yes. यहाँ पर हमने मास लिया था. अगर हमें यहाँ पर नंबर ऑफ मोल्स लगा दिया गया, मतलब कि हीट को ऐसे डिफाइन कर रहे हैं, Q इज इक्वल टू नंबर ऑफ मोल्स इनटू स्पेसिफिक हीट कैपेसिटी मोलर इनटू डेल्टा टी. दिस इज द सेम थिंग, इट्स जस्ट दैट कि हमने इसको रिप्लेस करके इससे कर दिया है. मतलब अब हम नंबर ऑफ ये मास ऑफ द बॉडी नहीं देख रहे हैं, we are just looking into the number of moles of that object inside the inside that matter, whatever it is. For the same thing, let's say if it has a mass m and n number of moles, then this becomes specific heat capacity with respect to molar or molar heat capacity. And now this again, molar heat capacity will not depend on the amount of material, but only depend on the nature of the material. ये सेम नहीं होगा, but they will directly be correlated, that's for sure. So that was molar heat capacity. Now there is something called और इसके पहले हम थोड़ा सा डिस्कस कर लेते हैं. Let's say you have this mass, you provided heat into it, the temperature rises. But what if you continuously provide heat into it और temperature बढ़ता ही जाए? What will happen is, at certain temperature it will go into a phase which is called liquid. उसका basic properties आपको पता है, but this conversion from solid to liquid or from liquid to gas is not just rising temperature, it is also giving or the energy is also spent in some sort of creating in, let's say the intermolecular distances were this much, this much, this much, but here the intermolecular distances are far away. अभी मॉलिक्यूल्स को इतना दूर दूर भेजने के लिए उनके अंदर का इलेक्ट्रॉनिक सॉरी एटॉमिक अट्रैक्शंस को हटाना पड़ा होगा ना, and that requires some work to do. That is why we have the difference between them. Let's say there is this ice at 0 degrees Celsius and water at 0 degrees Celsius. They are at the same temperature, but since they are at different states of matter, they will have some difference in their energies due to a higher distance between the atoms or the molecules of the water or whatever material it is. This change is nothing but latent heat. Latent heat. What this basically signifies is the amount of heat that you have to give to the system, not to resist temperature but to change the state. Now, latent heat of uh, fusion and latent heat of vaporization. Heat of fusion means from solid to liquid, and vaporization means liquid to gaseous form. So these two values will be different. उसको मान लेते हैं चलो latent heat of fusion and latent heat of vaporization. Now अगर मुझे कैलकुलेट करना होगा कितना एनर्जी उसको देना पड़ा, then this simply becomes Q is equal to latent heat of fusion into the mass of the object. अब इसमें टेम्परेचर का चेंज क्यों नहीं लिया हमने डेल्टा टी? बिकॉज इट इज एट द सेम टेम्परेचर दैट वी आर लुकिंग एट. We are not at all looking at the rising temperature or the falling temperature. We are just looking at the change in state. उसी फैशन में अगर हम यहाँ पर लिखना चाहें Q is equal to, or Q given for fusion or the melting of the object, and Q given the heat that must be given for vaporization is equal to latent heat of vaporization into mass of the material or mass of the liquid. All right. So this was latent heat. Now let me just quickly go through what we have all discussed. Okay, fair enough. Now let me come to something called thermal conductivity. See, let's say you have this object and both of them were initially at a certain temperature T. What you do is raise the temperature of this side. What will happen? The heat will transfer. Why? Because there is something called conduction of heat. When molecules are in contact with each other, there is something called conduction. Conduction means if you have an object in which अगर इस साइड ज़्यादा हीट दे दिया तो ये वाइब्रेशन ज़्यादा करने लगेगा, और ये वाइब्रेशन ज़्यादा करने लगा तो it will transfer the vibration into the other atoms, right? Why? Because it is vibrating and the other atom is directly in vicinity, so it will start transferring vibration, and that will lead to vibration on the other side, and this is called conduction of heat. अगर एक तरफ ज़्यादा heat है दूसरी तरफ कम है तो transfer ऐसे होगा. Now let's say the temperature here was T and sorry T dash and here T. What we can do is actually calculate at what rate is the heat transferring. It means the rate of change of heat at any of the sides. Now this will be actually equal to T dash minus T divided by something called thermal resistivity. Thermal resistivity or thermal resistance actually. Now this thermal resistance can be written in the same format as the can we compare this situation to the thing or the situation in which some current was flowing and there was this resistance and you had to calculate that I is equal to, sorry, yes, I is equal to delta V by R. This is exactly the same situation. इट्स जस्ट कि यहाँ पर चार्ज ट्रांसफर हो रहा था, यहाँ पर हीट ट्रांसफर हो रहा है, बट द बेसिक रूल अप्लाई स्टिल अप्लाइज हियर, वेरी सिमिलर टू ओम्स लॉ. अभी इसकी बात वापस से करते हैं. थर्मल रेजिस्टेंस इज इक्वल टू resistivity into L by A. This is called thermal resistivity, and the opposite of it, or the reciprocal of thermal resistivity, is called thermal conductivity. Thermal conductivity. Alright. So basically इसमें करना क्या है, I की जगह रेट ऑफ चेंज ऑफ हीट से रिप्लेस कर दो, वोल्टेज की जगह और चेंज इन वोल्टेज की जगह चेंज इन टेम्परेचर कर दो, और रेजिस्टेंस की जगह थर्मल रेजिस्टेंस कर दो, और everything remains the same here. All the laws applies in the same manner, and you can do that. So this was about thermal conductivity, and coming to something which is called radiation. First of all, before radiation, we will see, let's say there are two particles. This is one mass and there is this another mass. Let's say it is a higher temperature and it is at a lower temperature. Let's what you want to do is basically bring them to the same temperature. What you'll do is maybe touch them together. उसको उन दोनों को कांटेक्ट में ले आएंगे तो होगा क्या, जो मैंने बताया कि जब कांटेक्ट में होता है तो मतलब दे आर बेसिकली टचिंग ईच अदर, द एटम्स आर इन विसिनिटी ऑफ ईच अदर. अगर एक साइड के एटम्स में ज़्यादा वाइब्रेशन है और वो टच किए हुए दूसरे साइड के एटम्स को, तो वाइब्रेशन ट्रांसफर कर देगा. दैट इज कॉल्ड हीट ट्रांसफर थ्रू कंडक्शन. नाउ देयर इज दिस अनदर थिंग विच इज कॉल्ड कन्वेक्शन. कन्वेक्शन में क्या होता है, let's say you have something called, or something which is hot water, and what you pour into it is cold water. अभी cold water डालेंगे तो you generally know that cold water has a higher density than hot water. What it will do is cold water will start sinking into the hot water, and while doing that, you see, दोनों के बीच का इंटरफेस होगा, और इंटरफेस की वजह से थोड़ा थोड़ा कंडक्शन होगा ही होगा, राइट. बेसिकली ये वाटर का मॉलिक्यूल मिक्स हो जाएगा यहाँ, ये वाटर का मॉलिक्यूल मिक्स हो जाएगा, और वाटर मॉलिक्यूल्स एक दूसरे में मिक्स हो रहे हैं. अभी एक मॉलिक्यूल जिसके पास ज़्यादा एनर्जी था, अगर वो दूसरे में मिक्स हो रहा है दूसरे पार्टिकल्स में, तो होगा क्या, बेसिकली एट द एंड हुआ क्या कि जो भी हाई एनर्जी पार्टिकल्स थे, और सॉरी लो एनर्जी पार्टिकल्स थे इन द कोल्ड वाटर, वो चले गए एक इधर उधर, और हाई एनर्जी पार्टिकल्स ने रिप्लेस कर दिया. तो बेसिकली all the cold water particles and the hot water particles get mixed together, and due to which it results into a different temperature. Mix हो गया, heat transfer हो गया, right? So that is called convection, in which the transfer of heat is due to physical mixing of the molecules. कंडक्शन में एक्चुअली मॉलिक्यूल्स ट्रांसफर नहीं हुए थे, बस हीट ट्रांसफर हुआ था. बट इन कन्वेक्शन the high energy or the low energy molecules will mix with each other, और एक दूसरे में ऐसा amalgamate हो जाएंगे कि मतलब it will not make any difference कि उनका अलग अलग identity है. They will become the same thing, and that is called convection. Now there is this another thing which is called radiation, in which any particle which is at some temperature, maybe let's take the sun, since it has very high amount of energy, the energy actually from the surface, you must have learnt in chemistry maybe that in the atoms there are states, or there are different levels of energy in the electronic shells. और अगर किसी एटम के इलेक्ट्रॉन को ज़्यादा एनर्जी मिल जाती है तो वो जंप करता है into another shell, and while going down it releases energy in the form of electromagnetic radiation. Electromagnetic radiation means light of different wavelength, even if it is not visible. UV light, infrared light, X-rays, all that. Basically, they're all the same, having the same property, electromagnetic radiation. So that is why this type of release of energy in the form of electromagnetic radiation is called, or basically that is the phenomenon of radiation. Okay. Um, Now, coming to the laws of radiation, first of all, we have something called this Kirchhoff's law. What this basically says is, if you have a particle and it is at a room temperature or any temperature for sake, and the temperature of the environment is also T, then whatever heat it is absorbing, it must be radiating that heat. And the property with which, or the rate at which, or the property with which the how efficiently the heat is being absorbed or released is measured in the terms of emissivity or absorptivity. What this Kirchhoff's law says is, for any particle or any type of atom or any matter, for example, for any matter, the emissivity divided by absorptivity is equal to constant, and it is the same for black body radiation. What is this black body? Black body is a perfect body in which whatever amount of heat it absorbs at any temperature, it exactly radiates back the same amount of energy. अभी इसको black body क्यों बोलते हैं? Because if you are having some energy or absorbing some energy and releasing the same amount of energy, you will not lose any energy in the form of light, right? लाइट निकलेगा ही नहीं उससे, और कोई पार्टिकल जिससे कोई लाइट नहीं निकलेगा तो वो बेसिकली ब्लैक होगा. That is why this type of particles are called black bodies. Now, coming to Wien's displacement law, इसमें बेसिकली कहते हैं कि जब रेडिएशन होगा, जब भी रेडिएशन होगा, तो रेडिएशन के लिए लैम्डा वर्सेस the heat which is released. The graph looks something like, at a particular temperature T, if we decrease the temperature, what this basically will look like is, all right. Now, यहाँ पर हुआ क्या? Peak change हो गया, but the peak has also shifted. The lambda has increased when we decrease the temperature. So basically, this law says that as you increase and this is the peak, the lambda peak, right? The wavelength for the peak amount of energy radiated. So this law basically tells you that lambda maximum or the lambda peak is inversely proportional to the temperature. If you increase the temperature, the lambda will decrease for the peak. So this was about a very specific graph, and this thing that we left here is Stephen Boltzmann law. What this tells you basically is, at any temperature, if there is the body, then the body radiates energy which is proportional to T to the power 4. And we convert this into equality, it becomes sigma emissivity into T to the power 4, where sigma is the area. All right. Now, for a perfectly black body radiation, emissivity actually becomes 1. Why? Because emissivity is basically how much energy you are given and how much energy you radiate. For black bodies, they do it perfectly all right in the 100% format. That's why they have emissivity equals to 1, and that's why the law looks something like this for perfectly black body or black body radiation. And this is this Newton's law of cooling, which tells you that if you have an object at a temperature and the temperature outside of the surrounding is T dash, then the rate of change of heat transfer will actually be directly proportional to the change in temperature, which is this, and having a constant K. This is basically Newton's law of cooling. So I think we are done with this slide. Coming to thermodynamics part. Yes. Before jumping into thermodynamics, uh, what we are basically talking in this chapter is first thermo and second dynamics. It means the movement of heat or the transfer of heat changing into some other form, and things like that. In this thing, first what we will do is uh, laws of thermodynamics. All right. So the zeroth law, there is this something called zeroth law. It doesn't start with first. It actually starts with zero, zeroth law, because zeroth law is pretty basic. First law of thermodynamics was given, and then people said that there must be some very basic basement to it, and that's why they called it zeroth law of thermodynamics. And this basically says is if this A and this B, these are two systems which are in thermal equilibrium, means if two bodies are said to be in thermal equilibrium, it means they have the same temperature. And the second body is in thermal equilibrium with another body, it means having the same temperature. Then this law says is then these two particles should also be in the same thermal um, equilibrium. This seems to be very obvious, but this is basically the zeroth law. For the sake of it, you should remember it. Although it is rarely used directly because it is just a result which is obvious. So, zeroth law of thermodynamics, the most important law of thermodynamics is the first law of thermodynamics, which basically defines the energy, the law of conservation of energy. It basically says that if you if you put energy into the system, or if you heat the system, heat is basically the way through which you provide energy into the system, then it must result into some internal energy change or increase in internal energy, as well as some work done on the body. It is slightly different from the chemistry version, in which delta U was equal to delta Q plus delta W. But here, the way we have defined Q is different. That is why in this thing we have something in this format that जो भी heat हमने provide किया, that should go into एक तो उसका internal energy change कर देगा, बढ़ा देगा, और दूसरा उस पर कोई work done कर देगा. Okay. So this is called first law of thermodynamics. And there is this third law of thermodynamics, or sorry, second law of thermodynamics, which is basically a result. See, both these are not so important. The most important part is the first law of thermodynamics. The second law of thermodynamics says is basically अगर आपके पास एक हीट रिजर्वायर है, मतलब बहुत सारा हीट है इस सिस्टम में, और इसको वर्क कराना है, इस हीट को वर्क कराना है तो आपके पास एक इंजन होना चाहिए. इंजन इज बेसिकली द machine which converts one form of energy into another form of energy. This law basically says is that it is impossible to convert the energy from the reservoir into work done into the system with 100% efficiency. The efficiency can never reach to 100%. It means heat loss to hoga hi hoga. What this basically law is all about. So it is impossible for energy working between a cyclic process to extract heat from a reservoir and convert completely into work. That is the thing I said. अभी इसी को बोलने का दो और तरीका है. Basically same चीज they are saying that no process is possible whose sole result is the absorption of heat from reservoir and the complete conversion of the heat into work. वही चीज बोल रहे हैं कि कोई ऐसा प्रोसेस पॉसिबल नहीं है और 100% एफिशिएंसी वाला प्रोसेस पॉसिबल नहीं है जिसमें जितना भी हीट लिया उतना सारा का वर्क डन करा दिया. अभी थर्ड स्टेटमेंट क्या है? नो प्रोसेस इज पॉसिबल whose sole result is transfer of heat from colder object to a hotter object. इनडायरेक्टली सेम चीज बोल रहे हैं कि कोल्डर ऑब्जेक्ट से हॉटर ऑब्जेक्ट अगर करवा रहे हो हीट ट्रांसफर तो बेसिकली वर्क डन करना पड़ेगा और वर्क डन किया तो जितना एनर्जी डाला है उससे कम एनर्जी बचेगा और मे बी वर्क डन उससे कम होगा. Okay, so these three statements are one and the same. This is just a result, nothing numerical about it. Now, what we have covered till here is this much, this, and this. Okay, and this is the same thing I talked about, thermal equilibrium. It means when two bodies are at thermal equilibrium, they basically have same heat per unit mass, or when you bring those two objects to each other there will be no heat transfer between them. That means temperature same होना चाहिए तभी heat transfer नहीं होगा, right? If two bodies which are coming together अगर इसमें से heat कोई transfer नहीं हो रहा है इसका मतलब कि दोनों का temperature same है. This is what thermal equilibrium is talking about. Okay, now coming to yes, coming to something called this thing, Mayer's equation. First of all, this gamma that we define here is a property of any matter or any gas, actually, to be more precise, because these laws generally apply in practice to gases. So in gamma, what we define is Cp by Cv. What is Cp here? A specific heat capacity, and Cv is also a specific heat capacity. But what's the difference? Specific heat capacity of the system when pressure is kept constant. Pressure is constant, and specific heat capacity when volume is constant. अभी दोनों में difference है because let's say there is this system in which you are rising the temperature. If you are given that Cp is there or whatever the valuation that you did the change in the heat given and changing the temperature, whatever you did, you took part some of the specific heat capacity. अभी उसमें अगर वो वर्क कर रहा है सी, अगर उसमें तुमने प्रेशर कांस्टेंट रखा है मतलब वॉल्यूम इंक्रीज होगा, राइट? वॉल्यूम इंक्रीज होगा. अभी वही गैस है, अभी उसका वॉल्यूम अलग हो गया. इट मीन्स द इंटरमोलिकुलर डिस्टेंसेस मस्ट हैव चेंज्ड एंड the energy which is stored into the in the body or in the gases also depend on the intermolecular distances, and that is why ये वॉल्यूम चेंज करने से ना काफ़ी कुछ चेंज हो जाता है. एंड दैट इज़ वाई वी हैव टू डिफरेंट टाइप्स ऑफ हीट कैपेसिटी, specific heat capacity, one while keeping the temperature, sorry, the pressure constant, and another while keeping the volume constant. They result into different heat absorbed. उन दोनों के बीच का एक रिलेशन है Cp minus Cv is equal to universal gas constant R. Okay, now We also have something called entropy. एंट्रोपी का बस डेफिनेशन देख लेते हैं क्योंकि आई थिंक गिब्स फ्री एनर्जी एंड ऑल इज नॉट कमिंग अप हियर. It is in your chemistry, in which entropy has a larger role to play, but in physics entropy has quite limited role. अब entropy का definition ही होता है rate of change with respect to temperature. मतलब एक fixed temperature पे जितना change किया heat का, अगर उसको divide कर दें, मतलब the change in temperature per unit और per degree Celsius और per Kelvin, that is called entropy. एंट्रोपी अगर हो समझ में आ गया है तो we'll look into coming here. Yeah, I think that is the better part to explain it. Reversible process and irreversible process, जो बेसिकली उसका इंग्लिश टर्म का मीनिंग है वही है यहाँ पर. रिवर्सिबल प्रोसेस मीन्स हमने यहाँ से स्टार्ट किया और यहाँ चले गए, मतलब कि P1 V1 T1, मतलब कि एक सिस्टम है जिसका टेम्परेचर T1 था, वॉल्यूम V1 था और P1 उसका ये था प्रेशर, और इस पे कोई वर्क किया और इस पे कुछ प्रोसेस लगाया जिससे ये P2 V2 और T2 हो गया. अभी मैं वापस इसको सेम प्रोसेस का उल्टा करूं तो अगर ये सेम इनिशियल P1 V1 T1 पे आ गया, दैट विल बी कॉल्ड रिवर्सिबल प्रोसेस. बट अगर मैंने ऐसा कोई the process it has undergone through has led to some other P2 V2 T2 which cannot be directly reversed back while reversing the process is called irreversible process. ऑफ कोर्स घुमा फिरा के तो कहीं वापस लिया जा सकता है V1 T1 P1 V1 T1 पे, but while reversing the conditions which you had applied, if the um, initial parameters are reached, then that process is called reversible process. Now अगर reversible process हो गया है तो we will understand cyclic process as well. Cyclic process means, let's say you have something called P1 V1 T1 and P2 V2 T2 and third P3 V3 T3. You go here and then come back. This whole thing is called a cyclic process. All right, this is called cyclic process. And since you have come to the same P1 V1 T1 and T remains the same, then the internal energy of the system remains the same. There is no change, because internal energy of the system, you will learn later, is actually only proportional to or only directly proportional to the temperature. It is not at all related with the pressure and volume. It is independent actually. So this is called cyclic process. There is another thing called quasi-cyclic process, infinitely slow process that system remains in the thermal and mechanical equilibrium with its surrounding. Basically जो भी transfer हो रहा है, that is very slow, so that it basically is the same. It remains the P and V and T are almost the same. That is called quasi-cyclic process. Will not be much used in this chapter, but cyclic processes are very important from the graph perspective as well. ग्राफ में सीधा सीधा बना के दे देते हैं. For example, this thing, yes, let's discuss this one. Carnot engine. This is directly linked to the this thing, cyclic process. Carnot engine में basically करते क्या हैं? Let's say there's this PV graph. अभी इसमें just a second. Yes, there's this PV graph. When you perform isothermal expansion, what does it do? Isothermal expansion का मतलब कि अभी आइडियल का इक्वेशन लगाया PV is equal to nRT, अभी राइट साइड का चीज़ें तो चेंज नहीं होगा, they will remain the same because it is isothermal. Isothermal means the same temperature, constant temperature. Then P is inversely proportional to V, and this looks something like this. Okay, and now coming to adiabatic expansion. uh, just a second, I think I should draw it more sharply because it is almost come. Yes, yes, yes. Adiabatic expansion is basically this thing, and then there is this isothermal compression, and then there is this adiabatic compression. This is first part, this is second part, this is third part of the graph, and this is fourth part, linking to these four processes. This process is called, or this engine which it performs is called Carnot engine. The efficiency the efficiency of the Carnot engine is basically the heat that you have provided. Basically you must have provided from some heat reservoir, right, which must have some temperature T1. There is this machine for which, or this is this engine, and you are doing work raising the temperature of the sink. Sink means basically where the energy is going. Then Carnot engine is basically 1 minus Q2 by Q1, which is equal to 1 minus T2 by T1. This is the efficiency of the Carnot engine. Alright, so this is what we are talking about, and what we are left with is work done for various type of processes. For example, isothermal process. Isothermal means constant temperature. uh, Isochoric process means pressure constant. Isobaric process means volume constant. And there is this adiabatic process. Adiabatic process means external heat is not given or lost by the system. The heat remains there itself. For isothermal process, the equation for work done is in this format. The way we derive it is from the PV is equal to nRT itself. While the work done, first of all, let's discuss the work done for isobaric isobaric process, or isochoric. Isobaric means pressure is constant, and isochoric means volume is constant. Basically, in every work done, you have to do PdV. That is the equal to work done, integral of PdV. But in case of isochoric process, the volume never changes. So dV is going to be 0 in isochoric process. And that is why we have work done is equal to 0 in isochoric process. While in isobaric process, the pressure is constant. So pressure comes out, and work done is equal to P dV, and nothing but P delta V. So work done is equal to P delta V. This is the isobaric process. In the isothermal process, I already told you this is the equation which we derive from the ideal gas equation. We do the same thing. Work done is equal to integral of PdV. And there is this adiabatic process in which in the temperature also varies, but there is this thing which is PV to the V to the raised power of gamma is must be equal to constant. This is the basic law for adiabatic process. While gamma is the ratio of specific heat capacity at constant pressure divided by the specific heat capacity. This is the gamma. This is the gamma I'm talking about. This is gamma which will come into this equation. So this is the specific heat capacity ratio. When you do all that, you will play around with it, and calculate the work done in the same format, which is integral of pdv, you will be left with something in this format. All right. Now, what is left here is converts heat. Yeah, this is what we have discussed about, right? The efficiency of Carnot engine, and this is not so important, the efficiency of a refrigerator, because even Carnot engine is not so important right now, because recently, I think yesterday itself, it was removed from the JEE syllabus. But anyway, we are discussing it. Already it had been removed from the NEET syllabus. Refrigerator efficiency is not so important, but you should know about the efficiency of Carnot engine, because we don't know whether it is there in the JEE advanced syllabus or not. So that was it from this mind map. I hope you are able to remember some of the terms, because many of the terms are very synonymous, or looks very similar to each other. That's why the first slide itself is not so difficult to remember, and the second slide is more of a theoretical one, in which few equations, this one this one must be remembered, otherwise rest of them seems to be very easy. And you must also practice graph problems for this chapter, very important. All right, so that is all for today, and we'll see in the next one.